So I've previously made a video on using Stata to do PCA. In case you're wavering between whether to use Stata or Python for your PCA project, I'll leave a link in the description to my earlier video. But I strongly recommend that you give Python a go, even if you are new to it. It is better, in my opinion, in many ways, as I hope this video demonstrates. The book I got the example from is a nice to have, not a must have. The data are freely available even if you haven't bought the book, and you can get the results from this video or from the code that I will upload for you to my Discord server. I'll leave a link to that as well in the video description below. Okay, let's get on to the demonstration. The replication is applied to the principal component analysis or PCA example in the second part of chapter 3 of the book. The PCA is applied to the so-called HBAT data downloaded from the author's website. To follow my code, you will need to open the first tab of the spreadsheet labeled HBAT and copy the contents of columns G to S, rows 1 to 101. This captures all 100 cases of the 13 variables x6 through x18. Then you need to save this to a new file called hbat_data.csv in your Python working directory. After importing the required libraries and reading the data file, ensure that you have the expected 100 cases and 13 variables in your Python data frame. The PCA then begins with calculating the KMO scores. The Python code ranks the scores from lowest to highest to make it easier to identify the variable with the lowest KMO. In the book, the scores are on the diagonal of table 3.4, ordered from x6 to x18. And apart from that difference in presentation, which is minor, the numbers are identical, which thus achieves the first replication success of this video. Joe Hare and his co-authors specify that the minimum acceptable KMO measure is 0.5. If there are any variables in the KMO table that are below this, you need to eliminate the lowest one. Importantly, you must note that you can't eliminate multiple variables at the same time. You have to do this on a one-by-one basis. So we remove x15, which has the lowest KMO of 0.314. Notice how easy it is to find the correct variable using Python in comparison with the book's table arranged by variable names. Then we need to go back to the start. We do this by copy-pasting the cell with the KMO calculation code and running it immediately after dropping the x15 variable from the data frame. In the reduced set of variables, we observe that the lowest KMO is x17, and because it is below 0.5, we drop this one next. Note that x11's KMO is also below the cutoff. However, the one at a time rule is applied, so we keep x11 in the data frame for the time being, and only x17 is eliminated. Then we have the third run of the KMO calculation. As is becoming apparent, the PCA process is very repetitive. The resulting table of KMO scores replicates the diagonal of values in the lower panel of table 3.5. All scores are now above the minimum 0.5 level. Therefore, the next step is to run the Python factor analyzer command using the principal factor component or PCF method. This particular setting is required in order to replicate the book's results. I don't think it's necessary to get deep in the weeds about the differences between components and factors. In any case, the terms are used interchangeably throughout the literature. The eigenvalues as calculated by the Python code as well as the scree plot are exact matches with table 3.6 and figure 3.11 in the book. We continue to follow the book's thresholds and methods, so we retain 4 components. The next cell generates an unrotated factor matrix which replicates table 3.8. The main purpose of this stage of the process is to ensure that all communalities are 0.5 or greater. This is the case here, so there is no need to eliminate any variables on the basis of inadequate communality. Therefore, we proceed with a varimax orthogonal rotation replicating the upper panel of table 3.9. The only difference between this table and the Python output is that in the book the variables are rearranged in order of decreasing factor loading. We observe that each of the variables has a significant loading on only one factor, with one exception, which is x11. This is cross-loaded on factors 1 and 4. So x11 is now dropped from the data frame, and we have to go all the way back to the beginning and start the PCA over from scratch. We carry out the 4th run of the KMO analysis with the 10 remaining variables. All KMOs are above 0.5, so we calculate the eigenvalues and generate the scree plot, with the retention of 4 factors still being indicated. We generate the unrotated factor matrix and check the communalities, noting that all are above the cutoff value of 0.5. Finally, we carry out the second and final varimax rotation, replicating the lower panel of table 3.9 in the book. With all variables loading on only one factor each and at an absolute value of 0.7 or higher in each case, the quantitative phase of your PCA ends here. I've uploaded the Jupyter Notebook file containing this code to the Finance Fundamentals Discord server. See the link in the description. And if you've made it this far, thank you very much. That is it. I wish you everything of the best with your research project, and I'll see you in the next Finance Fundamentals video.